So, good afternoon. It's 12:15 and we're ready to get started in today's lecture. Now I have like double system here, so I'm following my stream using my computer, and I'm also following my stream using my mobile phone. As promised last week, I did visit in Giganti, and I was able to purchase the cables to connect my GoPro, this guy, to my computer. And yes, I was able to connect it, but it was not willing to cooperate with me. So I'm still using my old webcam. So I have no idea, like why not? So why it didn't is not willing to cooperate with me? But I need to figure it out. I need to spend more time for that problem next weekend. So hopefully next week, Wednesday, I have a stream that is camera-wise with a little better quality than today. Anyway, so I guess that this is okay, so it's understandable. So what happens today is that we're gonna discuss a little bit about finite element modeling and finite element method. We also gonna look a little bit about, what are the ways that we can actually combine the finite element model and method to model by the system dynamics. That means actually that today's lecture and the lecture next week are the ones that are clearly the most important ones when you're preparing yourself to first midterm exam. So they are very likely, I would say that 100% certainty, there will be several questions from this week lecture and next week lecture. And now regarding those questions, in last week team session, there was a common question about where are these missing questions, the possible questions you can find in a midterm exam. And those are now available in course Moodle side. So please take a look. And also I'm back in user rhythm, if you may. And a user rhythm means that each topic is first introduced by sets that I'm going to give you questions that may or may not appear in first midterm exam. And as promised, so how it goes is that the questions that can appear in a midterm exam are only the ones that are shown in my slides and the ones that are shown in a Moodle database. Well, those two things are exactly the same, so there's no differences whatsoever. And as promised also, you will have an opportunity to vote one question out of the 25, I think, that will not appear in midterm exam, and one question that will appear for 100% certainty in a midterm exam. And the voting action will take place in week 7. And now what I can see here in my first slide, is that there's a little bit of inconsistencies here. And the inconsistency comes from the fact that we will have 6 lectures. Well, let me change the color here. This is not too clear. So we have one more setting here. Let's make it a bit thicker like this. Okay, so it's going to be 6 weeks lectures prior to midterm exam. So the fatigue will not be a part of the first midterm exam, but finite element modeling, model reduction technique will be included in a first midterm exam. Okay, so with that, let's get started. And let's first summarize what we discussed last week. So last week we complete the case of 3-dimensional multivariate dynamics. And we concluded that one of the critical components there is a T matrix, the T matrix that relates angular velocity and time derivatives of tenorized coordinates. And that's actually is something that is extremely important for us because it allows us to express inertia components, inertia tensors, and other components using body reference coordinate system. And now with help of the T matrix, we can map that representation to be with any set of tenorized coordinates. And any set of tenorized coordinates Okay, so the microphone. So you said that there's something wrong in my mic today. Let me see. Okay, so is it a little bit too loud? Oh, what about now? Is it any better? It should be better now. Can you please let me know if it sounds better? Okay, I'm checking that is okay. So I was about to explain, and I'm going to take a look at the comment. Oh, now there is a comment came. How it is difficult. Still there. Hmm. Hmm. I don't get it. I don't get it. So it's so how it sounds then? It sounds that it's not clear. Uh, how can I fix that problem? Hmm. Lagging. As far as I can see, everything should be okay. As you know, my mic is connected to my computer, and the connection is showing the green light. Uh, all right. So let me ask you this: is it understandable? So can you figure it out? Ah, so internet connection perhaps again. So let me take a look what it says. Yeah, it says that audio stream. Okay, so yeah, I found it out that this is related to streaming. Let me. Okay, so it says that my audio stream bitrate is lower than recommended. They are recommending me to use a 128. So how the heck can I tune that? Just a second, I'm gonna spend a minute to try it. And if I'm able to do it, that will be great. And if not, then I don't know. Here it is where I can change it. Lock volume, filters, properties. I guess it is properties. Not that. Settings. Output. Source. Okay, let me check the audio. Yeah, what I'm doing is I'm correctly setting up my OBS. My OBS, but you don't get it. Like, where the heck that I can change that? Hmm. Mic. All right, I am not sure about that. Not at all familiar with this thing. Okay. Bitrate is not high enough. Okay, so let me see what my streaming is saying. So it's still complaining that we recommend. How the heck can I can change that thing? Excellent connection. Stream is healthy. Stream health is excellent. Okay, so I guess it's gonna take me a little bit too much time to do these settings correctly here. So I'm just all right. So because I'm not that experienced user of OBS. I can use it, but not experienced users. And making settings will take me quite a bit of time because I usually need to go and take a look at the YouTube videos that are explaining me how these modifications and settings can be made. And I don't think that I wanted to do it this time because we're middle of the lecture. So um, Or can you guys explain me where is in OBS I can change the bitrate? Maybe you know it better than I do. I know that you know that the problem is related to bitrate, and it's related to bitrate because that's what my streaming is complaining. But how to change that in OBS? Do you have any idea? So guys, please help me if you're doing the OBS streaming. So I guess that I need to select the mic. Oh, now it's okay. All right, so then we're just gonna go. But for next week, Wednesday, I need to take a look at this bitrate issue to make sure that it's better, because I got this complaint last week too, but I kind of thought that is not so serious. Anyway, so we were in this guy, so we were explaining this relation about angular velocity. So this is angular velocity vector expressed in terms of global coordinates, and then my G matrix, and then the angular generalized coordinates, not just the generalized coordinates, but the time derivatives. And this guy here is extremely important. So it's a G matrix that is doing the mapping, and that's going to be one of the questions that it could be asked in written exam. So what's the role of the G matrix? Yeah, the G matrix relates to your kinematics to any set of generalized coordinates, rotational coordinates to be more specific. And now you can see it here, like this guy here in the middle is obviously an inertia tensor. And now the inertia tensor is mapped to any set of generalized coordinates with help of G matrix. And now G has a variation, and the variation is such that if the angular velocity is expressed by using local coordinate axis, then you can use G bar. So that's what it is. So if you're wondering, like, what's the difference between the G and G bars? So it's just like how you do the mapping. Is it going to be with respect to global coordinates or with respect to local coordinates? And this is a possible question in this regard. How inertia tensor can be related to acceleration of rotational generalized rotational, oh my God, this is not well. So generalized rotational coordinates, so this should be taken off. Okay, this is how it goes. This is inertia tensor, and the mapping that can be carried out with help of the G matrix as it is shown here. So the one that will come here in the middle, so let me take the mesh off a bit. So the one in the middle is inertia tensor, which consists of mass moment of inertia, mass product of inertia, and it can be related to any set of generalized coordinates with help of G. And that, of course, tells you that the G depends. I mean, the G expression is a function of what kind of generalized coordinates you are using. And now I'm just gonna, one more time, I'm gonna open my chat window to see if there's any additional comments. Not this time. Okay, so then question that we're missing from last week's lecture was the follows. Why body deformation needs to be accounted in multi-body application? And the answer is because this is the way that you can, first of all, increase the accuracy. And second of all, you can get the quantities that are sometimes important, such like strains and stresses. So if you are dealing with the rigid bodies, of course, you cannot make any prediction about the strains and stresses. And strains and stresses in turn are important when you do that, when you're figuring out how the dimension of the structure is supposed to be. If you're making predictions about fatigue life, then you need to know the loading stresses. And you can only get it when you are considering structure to be flexible, deformable. Then the next question, how linear strain displacement relationship affects deformation of a cantilever beam. That is this example here. And remember then the case in the middle is such that you are assuming the strain displacement in this one here, U, and its relation to strain. That relation is assumed to be linear. And it means that if you're looking at the free end, the loading end of the cantilever beam, that remains in a loading line, which is okay. It looks natural if the deformation is small, and it looks very unnatural if the deformation is large. And to take that to be more natural, to be according to reality, this relation, strain displacement relationship, need to be nonlinear. So that's how it affects. So that's the answer to question number 14. Question number 15, explain the concept of lump mass approach. That's the one that you are replacing your one rigid body by a number of rigid bodies. And you will introduce the spring elements between these bodies, neighboring bodies. And the spring elements makes the structure system to behave like a flexible structure. Problem in this case is that it suffers from numerical difficulties, and one of the most severe numerical difficulty is numerical stiffness. I got the message from my GoPro camera. Never mind. Numerically stiff means that you have low frequencies and high frequencies, and those are typically a little hard to deal with when using a numerical time integration scheme. That's why what we're going to do next is that we're going to look at the floating frame reference formulation, which is conceptually very different, conceptually completely different. And how come? Well, it gets started from the kinematics. In the kinematics of a rigid body, we are used to deal with this equation, where we have first translation of body reference coordinate system, rotation of body reference coordinate system, and vector u bar, which is assumed to be constant. Now, what we will do in a floating frame reference formulation is that we're going to leave this assumption of u bar being constant. U bar will be actually consisting of two components. The one that is showing where the particle is initially located at, and how it is deforming, how it is changing its position as a function of time. And now because of this new guy here, u bar f, which is describing the deformation, everything will be changed. Everything will be changed. And that's, you know how it goes. If you change the kinematics, it means that, nothing going to be left from your original equation of motion. What you need to do is that you need to rewrite everything. And that's exactly what happens in a floating frame reference formulation too. Now, how this new guy that I just introduced, that I introduced last week, this u bar f, how that can be described? Well, easiest and most common way to make it happen is to compute this u bar f by using finite element modeling. Finite element modeling, that's the one that we're going to look at the next. Okay, let me see if I have any more summary slide from the last week lecture. I see that there is no more summary slides. Okay, what follows is the description of deformation, and it's all about this one single component that is needed in the kinematics. And to make it clear, so it's all about this u bar f that tells how is the particle location moving as a function of time. First, very important observation here is the fact that now we need to leave something behind. We need to give up something. And the very important thing we need to give up is that we cannot look at all possible particles when we're looking at the deformable bodies. Okay, let's go back to this, very basic. So this is a potato. So this is let's put it as a three-dimensional multi-body. So this is a potato-shaped multi-body system. And the way we're describing the multi-body system, or particles within the multi-body system, particles within this potato-shaped body to be more specific, was that we have this vector u bar. And vector u bar is the one that scans every single location within the boundaries of the body. And we can easily make it happen in case of rigid multi-body dynamics, because once we have a certain location, then that location is going to be constant with respect to local coordinate system. Now, in the case of flexible bodies, we have to limit the number of points, number of particles we're looking at. We need to use something that is called discretization. And the discretization means that this continuous volume that was here that we look at in the very beginning as a rigid body, we're just looking at the certain points. And we're looking at how these points can move with respect to each other. And we have to limit ourselves to that. So we cannot use these millions and millions of particles within the one body. That's going to be computationally not possible to do. We can only look at the certain number of points. And that procedure is called discretization. Okay, here are the questions. So when I'm explaining this subject matter, please put some effort to follow or to be sure that you can answer these questions. And right now you are unable to do it, but I will explain it a bit later how it goes. So question number 16, explain how polynomials can be used in the approximation of displacement. This is all about finite element method. This, by the way, is like a core of finite element modeling. And the core has a consequences. So when we are describing the displacement using polynomials, we end up to have something that is called safe function matrix or safe functions. How those safe functions can be derived, that's what I'm going to explain to you next. Then, excuse me, related to polynomials, there's a questions about Pascal's triangle. This is how you're selecting the polynomial expression. How it goes, that I will explain right after I have explained about what is the role of safe functions and polynomials. And then something very basic, which too is related to this polynomial expansion and safe function. And that is, what is a convergency rate? What the convergency rate means in finite element method. And then what is that the safe functions are describing, like a little bit of physical interpretation about safe functions and how to obtain them. You know that these two guys are heavily related to question number 16. So those are the possible questions. And again, list of possible questions will be available in Moodle database. Now, I'm making assumption here that you are not familiar with finite element modeling. If you are familiar with the finite element method, stay tuned, because I would like to explain the finite element method a little bit a different way that you are usually learned or usually dealing the method. So I'm going to get started from basics. You know, the finite element method is a numerical method where, strictly or broadly speaking, we are solving a differential equation using approximates. Well, to be more closer to real life, it means that we can solve the problem of structural strength about the displacement by using something that is small pieces of solution. These small pieces of solution are called elements. One single element typically is not the solution, but once you keep on adding these elements, like using almost like building a structure by using Legos, and the Legos are these elements. Then once you keep on adding the elements, then you could get a good approximation about how the system behaves. And this is exactly the concept in the finite element modeling. And these elements need to be combined together. They need to be related together. And the way they are connected together will be points. And these points will be called as nodes. Now, how it looked then? It looked in the real life that you have a potato-shaped body like this. On top of the potato-shaped body, there's like a fishing net. The fishing net, I'm sorry, the drawing is not so great quality. But anyway, so there's like a fishing net. And this is the typically finite element mesh that represent, let's say, plate elements. This is now considered to be thin plate structure. And each one of these elements is a piece of the solution. And the piece of the solution is such that if you look at this particular element, so it's a rectangular shaped element, and it has 4 nodes. And these nodes makes it possible to combine this element to its neighboring elements. So this is how it looks. Now, again, keep in mind that this is, mentioned whether it is mentioned here, small region. So more small problems. This is the one that is like a piece of the solution, and you keep on adding this piece of solution, you get the full solution. And in a beam-like structure, if we're looking again like a cantilever beam, we can have a node here, and we can have like lines that are connected together in dots. So this guy here is one single element that is connected to neighboring elements by nodes. This is how they look like. Now, convergency, that we will discuss in details a bit later. Oh, I can see that I was blocking the view a little bit. Was there a comment about that? No comment about that. Convergency, which we will discuss in details a bit later, goes in such the way that if you have here a graph where this is a number of elements, this number of elements that is telling you the final solution. And then let's say hypothetically the correct solution is somewhere here. So that's where the correct solution is. And this could be the case of the cantilever beam. A cantilever beam could be loaded in a way that it is loaded in a freehand. And then we are looking at, for example, the final displacement here. So this could be the final displacement. Now, how we can do this work is that we can have a rough mesh here. The rough mesh at the worst possible scenario, or one possible scenario, is that there's just the one element that describes the entire structure. This is a very simple problem, so you can get a good solution in this simple problem by using one element. But generally speaking, when using a low number of elements, your solution is not so great. So you're not getting the solution that is acceptable. But once you keep on adding elements, let's say that now instead of having one element, there's 3 elements, your solution is getting to be more acceptable. Once you keep on adding the elements, your solution gets better and better and better, and finally it converts to this correct solution. This one here means convergency rate, like how fast you can reach solution that is considered to be acceptable. We will get back to this because this is one of the basic things in finite element modeling. But again, keep in mind that you typically need a certain number of elements to get an acceptable solution. Certain number is unclear language. And it's unclear language because there's no way to give you specific answers. And the reason behind it is that, that the problem varies. There's so many different variations that there's no way to give you an answer that covers all possible scenarios. All right. Now, what this finite element method is then about? The finite element method is all about how is that we are assuming particles between these nodal locations to behave. So that's all about the finite element method, or displacement-based finite element method. And I know that I cut the corners. So those ones that are really deep in the finite element modeling could be like, oh, no, it's not like that. I don't care this time because I want to make things as simple as possible. So one more thing that I need to do here is that I noticed that I somehow changed the configuration of my system. So I need to put this a bit bigger. Just a second. Like this. All right, so I was about to explain that the finite element method is all about how are life between these nodal locations. So it means that if you have here a beam element, the beam element that has 2 nodes, you have to make some kind of approximation how the particles between these nodes behaves. And this what tells how good or bad is your finite element method or element, to be more specific. And this is very much different that you are used to heard of before or learned before, because before, I'm sure you heard this story that finite element method is same thing like introducing spring elements. There's node allocation, that the node allocation plays a significant role, and then something that is between these nodes is like springs. No, no, that's not the case here in the finite element modeling. It's all about how you're predicting particles between these nodes to behave, and it's not simple. The easiest way to make this prediction is using polynomials. You could use many other means, and there are methods that are using other means than polynomials, like NURBS, non-rational uniform p-splines, possible. You could use trigonometric functions. Yeah, you can do that. Never really mind. It really doesn't matter what you use. That what matters here is that how is it you're predicting life between these node allocations to take place. And it really depends on what are the possible ways that these nodes can move with respect to each other. That's what tells. That's going to be something that is called element degrees of freedom, or nodal degrees of freedom, to be more specifically looking at the node allocation. Now, I lost the comment window. I need to put it back to make sure that if there is no comment so far. How is your story so far? Is it like okay, or you heard this story a million times before? Okay, no comments. Anyways, there will be in-class quiz momentarily, so then I will check like how is your level of knowledge. All right. So we were about to look at this life between the node allocation, and now let's say that we are dealing with well, let's put it very simple. Let's look at we are only considering the system where the node allocation here can move back and forth like left and right. So this one here has a 1 degree of freedom. There's a comment, I need to take a look. Difficult. Yeah, I know that it's difficult, but I'm going to repeat this over and over again, so no worries, no worries. Those of you that are having the extensive history in finite element modeling, you may be like, yeah, this is so simple. But again, like I said earlier, it makes sense to stay tuned because you could get a little bit different point of view to finite element modeling. All right, so I was about to explaining the system that these two node allocation can move back and forth. It means that this one here, this node has a 1 degree of freedom. This node here has a 1 degree of freedom because it can only go left and right. All right. So if this has a 2 degrees of freedom, the simplest way to predict how particles between these nodes, let me make a dot line here. I don't know if it is clear. Well, anyways, what? Oh yeah, I what I did was that I got the voice to my headset that it was disconnected, and then right after that there was a voice again which says connected. So somehow it was all about my headset connection to computer. I need to be more familiar with the computers for sure. This is my weakness. And not my weakness. Of course I know quite a bit about that, but the streaming business is something that I'm still a beginner. And now if I want to be a world famous YouTube character or however you call them, I need to learn this thing. But I think that this finite element multibody has a potential to be like collecting millions and millions of viewers. I think so. Now I get confused, but I was about to explaining like how is that we can estimate the particles to move, all particles actually to move between these node allocation, and all particles again means that there's going to be a lot of points we need to look at. So we need to build a continuous function that shows how these particles can move with respect to each other. Now, if we're going to use a polynomial, we can make a polynomial expansion in such the way that we can have two unknowns in our polynomial expansion. And two unknowns will be something very simple. So it would be the one that is showing here. So it will be, oh, hold on, I need to take this off. All right. So it will be polynomial expansion such the way that there is a, first of all, like a constant function, a constant parameter, and then there is the one that is multiplied by x. So this is going to be a polynomial with two unknowns. Unknowns are a0 and a1, and they correspond to the nodal degrees of freedom, the ones that is in this system. If I would add one more node here in the middle, like the one more node here in the middle, that would mean that my element here would consist of 3 degrees of freedom. 3 degrees of freedom. That would mean that I would be forced to add one more component to my polynomial expansion. That will be a2 multiplied by x power 2, because these x goes in a row. They actually come from the Pascal's triangle, which we can take a look at a bit later. But shortly, the Pascal's triangle is something that has a component like this. So xy, this is a planar case, I mean two-dimensional case. X power 2, you can use this kind of polynomial selection when you're building shape function for, let's say, plate element. And so on and so on. This goes like, as far as you want. So there is no limitation. This one is called Pascal's triangle. And now what I did in the case of 3 degrees of freedom, I selected my polynomial coefficients here. And these coefficients have to be multiplied by unknowns. And now is pretty much going down to how to solve these unknowns, a0, a1, a2. And once I know that, then the polynomial will tell me how is the particle moving between these nodal locations. How come? Well, look at this. This is telling me the displacement that is a function of x. So this is my representation of displacement. And if I know this, then I know how is a deformation. And this is all about, this is pretty much finite element modeling in a nutshell. Some buts. The first but is that, but what about this A1 and A0 and so on and so forth? Like, what is the physical interpretation? Well, that's a good question, because they don't have a clear physical interpretation. So the first thing that I want to do here is that I wanted to express these A's, these unknowns, to be more clear, or to have more clear physical interpretation. Well, the one that has a clear physical interpretation is obviously this nodal displacement. This node that can go left and right. So maybe instead of using these unclear parameters, A0, A1, A2, maybe I can use nodal degrees of freedom. Yeah, I can do it. I can do that. That's what I'm going to do next. And when I do that, I'm going to get something that is called shape functions. And the shape functions are telling me if how the particles between these nodal locations, how is that they moving with respect to each other. All right, I know that this is a bit challenging, and no in-class quizzes, no funny stuff. But hold on. So I'm going to have, let me see, two slides, and then the first in-class quiz. So try to push yourself. Don't start browsing with something interesting website, but stay tuned, because soon we're able to close the case. And then I'm going to repeat the whole story. And that's going to be something that I most probably will ask when we are going to midterm exam. All right. Now we're going to move on to mathematics. So this was my polynomial expansion. Now what I'm doing here is that I'm expressing my polynomial expansion by using two vectors. The vector that consists of my unknowns, which is this guy here, a0, a1. And these polynomial coefficients, 1, an x. 1 and x, because Pascal's triangle. All right. So this is just an alternative way to express the displacement within this element. So this is a displacement. This is still like estimating how different particles are moving between these nodal locations. Okay, so what is the information that I have? I do know where is my node are located in the very beginning. I know that when x is equal to 0, that's where it's going to be my first node located. And the first node will be noted as a U1. When x is equal to L, that's my second node is located at. And here it is. So this is x. And when x is 0, obviously we're in this point. And when x is L, we're obviously in this point. Okay, let's use this information. So let's substitute 0 to my original equation that was written in the previous slide. And what I'm going to get as a result is obviously A0. And when I'm going to substitute L to where the x is located, I'm going to get the equation, which is A0 plus A1 multiplied by L. Okay, sounds good. So let's express these two equations in a form of matrices and vectors. So, okay, I have here nodal degrees of freedom, my node displacement, and then the matrix, which came from this equation here, and then my original unknowns. So these are the one that where I started. But I don't want to keep them anymore in the system because I don't like how they are, because they have this problem that they don't have a clear physical interpretation, and I wanted to have it clear. I wanted to understand the results. Okay, so the only thing that I need to do is that obviously I need to substitute this guy to this equation. How can I make it happen? Well, I just need to invert this matrix here. Once I do the inversion, then I'm ready to go. I'm ready to do the submission here. And this is now how my shape functions look like. So not now, but once I do the math. So once I computing everything, so I have a approximation about the displacement. And the displacement will be expressed by n, which is my shape function matrix, vector in this case because we are looking at the planar case, and nodal degrees of freedom. These are the nodal degrees of freedom. These are the shape functions. They are telling me how particles are moving if one node is moving left and right. That's about it. And this is all about the finite element method. You can make this polynomial expansion in a different way, and you could get a little bit of different assumption how the particles are moving. That's okay. And that's exactly what can be done in a finite element modeling. But really what is important is to understand that there's a life between the nodal location, and the life between the nodal location defines how is your finite element. Okay, so now I got these two shape functions, and these two shape functions are, I have the visual representation how they are. This is not very clear physical interpretation because I kind of plot them in a planar space, and seriously they are just a line. They're just a line. So, but just roughly how they are. If this is your original particles, this is your nodal location 1. This is your nodal location 2. These are just the two particles, which are much more than these two. How they are behaving when you look at this shape function, they're behaving in a way that if you're moving this first node, this direction, this is following and this is following according to this equation. So they are following in a linear manner. The similar way, if I'm moving my other node left and right, how these other particles are following this displacement. Bit confusing to understand how they are, but it becomes clear when we're looking at the beam elements. Okay, so it's all about polynomials. So everything gets started in a way that you kind of defining how many nodes you have in a system. You can have these boundary nodes. You can have internal nodes as well. Like the example that I explained it to you a bit earlier, I had one internal node. Now, if I have two internal nodes, it would mean that I have 4 degrees of freedom in my system. So I need to select the polynomial such the way that there is going to be 4 polynomial components. And now I got the comment. So let me take a look at the comment. Oh, yeah. So I'm plugging that again. Sorry about that. Yeah, this is something that when I'm writing stuff to my PowerPoint, of course, I don't plug myself, but I'm plugging the view from you. Thank you for letting me know this. But anyways, so if you have 4 nodes, 2 boundary nodes, 2 internal nodes, that would mean that you need to select 4 polynomial components from your Pascal's triangle. And a Pascal's triangle, if we go back here, would be this guy. So you would need these components. Okay, so there's going to be in-class quiz. So let's see how well we're performing in that in-class quiz. It's not going to be easy, but it's pretty much what I just explained. Okay, so I have here 4 node spring element. The spring element means that the nodes can only move left and right. How is the polynomial expansion for this kind of element? And the key or the way to solve this problem is that you need to first identify how many degrees of freedom you have. Once you know the number of degrees of freedom, then you can identify how many polynomial components you need. So it pretty much goes down like, is it 2, 3, or 4? And once you have the solution for that, then you can select the correct answer. And I'm going to put my, hold on. I'm going to put my in-class quiz on, and I think that it is on. It is on. I can see that I have 42 students in the system, which is like, wow, how come it can be that many? But anyways, I got one answer already. I just need to look how to put this visible. Oh, and the game is on. The first guess is 65. 65 is maybe a high side, I think. I'm personally predicting a bit lower than that. But we'll see. We'll see. And in class quiz, let me put it in OBS. This is a new thing that I learned. So I can have 2 windows, and then I can activate and deactivate them nicely. Like now this should be, here's my in-class quiz. Look at this, getting better. We got the, okay, so we got the guess that is 95, which I appreciate. It's a high, but I'm more like myself, like 30, what I would say, 32 perhaps. I'm gonna hide this one more time. Oh, not this one, but this is the way to hide it, so that you can take a look. My personal guess is look at that, 35. 35, that's low. We'll see. All right, and then there's going to be one more discussion about the finite element modeling, and then yeah, I need to discuss a bit more about this convergence rate. But I cannot do it right now. I need to look one more thing. All right, so now I'm gonna put the circuitry back on 24 answers. I think this is pretty much it. So I'm gonna wait a little while, and then I will show the results. 26 students. Okay, so what do you guys say? Can I just close the game and see how well we're performing? That's what I'm about to do. Okay, so we got some last minute answers. Okay. Look at this. 70, 70, not 17, but 70, 70. That's great. That is really great. Okay, so let me go back to the chat window and see if we got any winners this time. Where is my chat window here? Okay, so what is that you guys are guessing, or what is that you're saying that is acceptable? Okay, I got 71. 71 is winner. How come this same individual that was guessing 71, he seems to be winner like pretty much every single game? Like, how come? I'm not gonna mention the name because this is a public stream, so I don't want others to know my student's name. But good guessing again. So let me see if there's any other winners. 72 will be considered as winner as well. Good stuff. 73. Extra point. Okay. Let me see if there's any other comments, questions. Can't see the answer. Yeah, I can count the. Did I miss 69? Because I think that I can't. No, you're right. 69. Extra point. Sorry that I missed that. Okay. So those are the. So I got a total of 4 winners. The one that is guessing. Well, I don't remember the numbers anymore, but four ones. The last comment, you got an extra point. All right. So what next? Okay. Now we know that we have polynomial expansion, and this is extremely important. So we know how the particles are behaving when one node is moving in a certain direction. So we know how is a deformation within the element. What is it we can do in this information then? Well, we can do quite a bit in this information. We can express something that is called stiffness matrix using this information. And what is that we need in a stiffness matrix is that we need to have a relation between displacement and strain. And once we have a strain, then there's many different ways how we can proceed from that. We could just compute the strain energy, like simply the strain energy, which will be like, if using the matrix notation like this, maybe a little overly difficult, but this is a strain. This is elastic coefficients, I mean the vector of elastic coefficients, and this is going to mount integrating that over the volume of the element. That's going to give me my strain energy. And if I differentiate my strain energy with respect to my unknowns, which are nodes, I know that I'm using the incorrect notation here, but let's put it like W here. That's going to give me stiffness matrix. That's what I'm going to do next. So we need to find the first relation between strain and displacement. And once we have that, then it's very mechanical. Actually, these two is already very mechanical. So the only thing you need to get in finite element modeling is to get this U. And again, how is that you can get the U? I know that I'm plucking a U again a bit. How is that you can get the U? Is that you need to identify what is the number of degrees of freedom. And once you know the number of degrees of freedom, then you're expressing this number of degrees of freedom using polynomial expansion. That's it. I need to move this direction. I was moving the wrong direction. So, how is this is how the elastic forces can be computed. Yeah, well, this is a pretty much story that I just mentioned. the virtual work done by elastic forces. Now this is virtual work, so I could use energy or virtual work, doesn't really matter. And but again, look at what I have here. I have this strain, so I have to be able to relate my strain and displacement. Strain and displacement. And once I have my strain, then it's just mathematics. I can use this chain rule of differentiation to express this delta of displacement by using delta of nodal degrees of freedom. So all that will be more or less mechanical. So I'm not going to explain too much about the details, but instead, let's look about the big picture. First relation, extremely important. How is this displacement strain relation? And the displacement strain relation is the one that it is in this particular case explained like this. So it's going to be displacement differentiated with respect to coordinate x, because I'm looking at simple spring element, the spring elements that only can contract and extract. So it's going to be this simple relation. And when I'm substituting here the displacement notation such that is a safe function matrix vector this time multiplied by nodal degrees of freedom, I can find the relation between the strains and nodal degrees of freedom. This displacement this time will be simply obtained by differentiating the safe function matrix vector again with respect to my coordinate x. This one here that is relating strain and displacement is often in a finite element literature called as a kinematic matrix. Often in a finite element literature is called as a B matrix, kinematic matrix, and is doing this relation. And once you have the relation, that's it. Then it's just a matter of substitution. Matter of substitution how? Well, in a way that you just substitute the strain here and here. There you're gonna, here. And once you do all this substitution, what is going to be left is this guy here. Now here is my kinematic matrix with the transpose and my kinematic matrix without the transpose. Once you do the math, once you compute it, then you can get something that is going to be called as a stiffness matrix. Okay, that's my final outcome. But remember again, whole story started from the polynomials. And it started from the polynomials, and with help of polynomials, you were able to make a prediction about how is a displacement as a function of nodal degrees of freedom, and this relation was expressed by using safe functions. We're going to take a look at one more example, and this one more example should make it clear, like what is this safe functions. One more thing about these finite element models is that, of course, forces too need to be expressed in terms of unknowns. And unknowns in a finite element modeling are these nodal degrees of freedom. And you can do that too by using a safe function matrix. So you're following this idea. I'm not going to look at that in details, but you can use the safe functions to express the forces that are imposed anywhere in the structure in terms of nodal degrees of freedom. Okay. Okay, and this is finally how the finite element static equation look like. So this is, to put it in a more familiar form, is a stiffness matrix multiplied by nodal degrees of freedom is equal to external applied forces. Put it in a context one more time. I have the cantilever beam, which I'm modeling by using number of elements. This number of elements will eventually form my stiffness matrix. How? That I will explain a bit later. And then you have this force, this one here, this guy here. And what you're doing in a finite element modeling is that you are solving the nodal displacement. And nodal displacement you're solving by simply inverting your stiffness matrix and then multiplying your forces by inverted stiffness matrix. Hard stuff. Not easy. Not easy. But important too. Extremely important, because finite element modeling is a core knowledge of mechanical engineering. It is so much used in many different disciplines, not just in a structural strength, but also in other disciplines. So it's very valuable tool. So this is a short introduction to finite element modeling. Now, I mentioned earlier today about this convergency rate. And the convergency rate means like how fast you can get, what is the number of elements needed to get an acceptable solution. And many cases, the convergency looked pretty much like I was making this picture. Oh, I touched something. I guess that I went one slide ahead. Okay, many times the convergency looked like if this is a correct solution, convergency looked pretty much what I was depicting earlier, something like that. But not necessarily. Convergency could be also coming from this side. Or the convergency could be even fluctuating around the correct solution. And to see whether or not your solution is correct, well, the easiest way is first of all to know how is your convergency rate. And typically the convergency is the one that was showing in the very beginning. And now if you're making a model with a certain number of elements, like this number of elements, and you're increasing the number of elements, if the solution is changing, then you do know that you don't have a converged solution yet. And you need to keep on increasing the number of elements. But if you're increasing more your number of elements and you have solution which is more or less no changes, then you can be guaranteed, almost guaranteed, that your solution is converged solution. And here is very important lesson. It's really, really hard to know if you have a acceptable solution in your finite element method. The best way to do it by making a more dense mesh and see if that affects the results. And if it does, then you even need to go further. You need to make one step, you need to do one step ahead. You need to check like if this is still affected by more dense mesh. Now there's a comment I need to take a look at that. Yeah, we never know the right solution. So we never know the right solution. That is a problem in a finite element method because you're using finite element method in a problems that you cannot solve by using pre-calculated tables or some simple other methods. So basically, the only way to do it, to know like if your solution is acceptable, is to make your mesh to be more fine, and then see if the solutions are affected. Now the problem may be that it's worst possible scenario, you can have a convergency rate that is fluctuating like this. And now if you really had a no good luck, I need to change the color to make this more clear. Okay, so you can get the point that is here, and then you're making more dense mesh, and you get the point here. And the solution is no changes. And you say, okay, this is my correct solution. And you said that you see that is not. But this is more theoretically possible because all the commercial software, they make sure that they pretty much behaving like this. They're converging the correct solution from this side, not from this side. But minimum requirements for this convergency. Well, minimum requirements for the convergency is that you first of all need to make your polynomial selection such the way that you have to have this A0 involved, because A0 means that you have element that is capable to describe rigid body translation, and which is this time is not really rigid body translation, but it means that element orientation can be anything you want. It can be translated anywhere you want, and it's not producing any strain because of that. This is very, very important feature because if the element is without no strain here, it should be the same it is here or here or here, and the way to guarantee that is to use this component. You also should use this component because this is the one that is guaranteeing the constant strain. Constant strain is something that is another minimum requirement. And the third minimum requirement is that the shape functions have to be continuous enough to be able to compute components needed in a shape function. And now we're using the first order differentiation, so the linear polynomial is okay. If it would be second, if the the partial differentiation would be second order partial differentiation, then you would need a bit higher components, second order polynomial. This is a short highlight, but the convergency rate means this one, and this is the one that I could ask. What was another question? I think I need to go and check. God damn it, I moved that a bit. Where's my other questions? Role of Pascal triangle. Pascal triangle, remember it was this one that you can use to do the selection of polynomials. And now comes something quite interesting and something that is a little bit personal story as well. So let me just finalize the Pascal's triangle and then I will tell you that story to you. Like this. It's kind of recommendation that these polynomials should be selected from the order that they appears in Pascal's triangle, but not necessarily so. You can also make some selections. Let me try to turn it in a way that you can see my drawings a bit better. I think I need to go this direction. Okay, so you can also do the selection. I'm going to check the chat comment in a minute, but if you have this kind of element which needs 4 components, and let me make it more simple. 3 nodes, 2 boundary nodes and 1 internal node, which means that you need to select 3 components in your Pascal's triangle. You could select this guy, and this guy, but you could do also, these are like mandatory components to make sure that the convergence is correct. This is not mandatory component, and because it's not the mandatory component, what you could do is that you can select, instead of x power 2, you can select x power 3. And sometimes the good elements, the element with a high convergency rate, are built exactly this way, in a way that you don't select the polynomials consistently from the Pascal's triangle, but you're selecting them selectively, and then you just try how well they perform. Okay, let me check the comment. Okay, so my head, so it was all about my head. Sorry about that. Next time I promise to make my head to be smaller. And that's easy because, just the tuning, making a tuning. And I think it may be more pleasant you to follow too. This personal story related to these safe functions. Maybe I have never mentioned this to you earlier, but once I got my doctorate degree, I spent my postdoc period, made my postdoctoral studies in University of Illinois at Chicago, UIC. And my supervisor in UIC he's still working and he's still active in UIC, was Ahmed Shabana, so very famous professor Ahmed Shabana. And he gave me an assignment that was related to flexible multibody dynamics. And the assignment was kind of simple. It was to select the polynomials, more specifically, safe function matrix for a plate element. And the plate element was not a typical plate element, but it was a plate element such the way that it was like this rectangular shaped plate element, and each one of the nodes consists of 12 degrees of freedom. 12. It's possible to make something like that. It just means that it has a little bit of harder physical interpretation of what these 12 degrees of freedom means. But they simply means like fiber deformation, internal fiber deformation within the plate. Okay, so 12, 12, 12, and 12. That's a total of 48 degrees of freedom. So 48 degrees of freedom will have to be selected from the Pascal's triangle. And you know that in that case, the Pascal's triangle goes really heavily down here. And that was my assignment. And it wasn't easy. It wasn't easy at all because, what happened to me when I was selecting these polynomial coefficients from the Pascal's triangle. I was able to do these all these computation. Let me make this clear. Oh, not that. God damn it, now it jumped again. So hopefully it looks okay. All right, so I was able to make like this relation, no problem at all. So I was able to relate the nodal degrees of freedom and these unknowns polynomial coefficients. But the final step, this one, converting this matrix, which at the time was 48 times 48. And of course, you cannot convert that size matrix by yourself. So I was have to use a symbolic math tool. But first manually make the matrix that is size of 48 times 48, and then converting. And the symbolic math tool said singular. You cannot do it. And then you change the settings. You change another set of parameters, polynomial coefficient. You build the 48 times 48 matrix. You convert it, and singular. And you do it again, and singular. And honestly, I spent, I think, 2 months, at least 2 months in my life to doing this work. I made an automated code and everything, and I tried everything, and I was desperate. It looked at this is problem that cannot be solved. And then one day, it was invertible matrix. How come? Pure luck, I think, but it was almost like a nightmare. So I have a true personal experience about safe function matrices. Okay, that was my personal experience about safe function matrix. I have another story related to this University of Illinois at Chicago, which I will tell you a bit later, which is more educational than the struggling with the safe function matrix. Okay, now I'm going to check if there's any other comments. No other comments. Sorry that I keep on putting my head, blocking the window by my head. So one more thing, which I will do is that I will shortly show you how is a safe function matrix associated to beam element. Why? Because it's so much more easier to understand the role of the safe functions when looking at beam element. All right. Again, I want to make things to be clear. And by the way, this is where I'm going to stop today. I know that I have 15 minutes left, but I'm going to explain this story to you, and then I'm pretty much done. All right, so I have here beam element. Beam element consists of two nodes. Okay. These two nodal locations both have 2 degrees of freedom. So these 2 degrees of freedom are displacement in y direction and rotation. Hold on, I need to take some coffee. Here in my node number 1, I have the same degrees of freedom. So it's only can move in a y direction, and it only can rotate. And the length is of course L. And then it is known that the displacement in the y direction and rotations are combined in this partial operation. So that's going to be my my element here. So a total of 4 degrees of freedom, because 2 degrees of freedom are associated to first node, 2 degrees of freedom are associated to second node. And again, there's displacement in transverse direction and rotation. All right, first question. How is my polynomial expansion? Polynomial expansion, if I want to be consistent with Pascal's triangle, I simply will go and select my, where is my Pascal's triangle? Here. I'm going to select the 4 components here. 1, x power 2, x power 3. That's it. That's exactly what I'm going to do here. So let's take a look how it is. Here. So it's going to be my polynomial expansion. So hopefully the font is large enough. So I have here 1, a0, a1 multiplied by x, a2 multiplied by x power 2, a3 multiplied by x power 3. And I can express this by using vectors like shown here again. And the next, I'm going to use the information that I have to create the four equations. The equation that I have is information related to where the nodal nodes are located initially. So x going to be equal to 0 when I'm looking at this first node here. So I'm going to get this. This is my first. When I'm substituting this information, this is to here. This is what I'm going to get. Then I'm going to take a partial operation of this one here with respect to x. And I'm going to get my rotational degrees of freedom. And when I'm substituting x to that, x is equal to 0 to that, to be more specific. This is my second equation. And then I redo the same for the equation that is located in a place where x is equal to L. All right. What I'm able to get as a final product is four equations, four unknowns. These are my unknowns. That's what I'm after here. Okay, and I guess that you know what I'm about to do next. I'm now here relating my nodal degrees of freedom and my polynomial unknowns. And really the thing to do here is to take this matrix, that the one that was in my case was 48 times 48 inverted. And once I'm inverted, this is how it looks. This information then finally will be submitted here. And what we're going to get as a result is the safe functions. Safe functions. And now the safe functions have very unique features. And it's easy to see these unique features when we are looking at how are these safe functions in a case of beam element. Now, here are my four safe functions. These are, or this can be written like it is shown here. And when I plot them out, when I print them as a function of x, and the x is here element length. And my first nodal degree is the displacement in the y direction. And now you see that this is safe functions that predict that displacement. Two important observations here. You know, this safe function will is first of all continuous. So it's predicting how each one of the particles between these nodal locations, how they're behaving, because you know you can go anywhere you want in this line and you can get the prediction how these particles are moving. Another greatly important observation is that the safe functions are affecting only to one nodal degrees of freedom at the time, because rotation in this end is 0, displacement in this end is 0, and rotation in this end is 0. So it's only affecting this one single degrees of freedom. When I'm looking at what about the rotation in this end, you know, this is how particles are predicted to move. Again, here the displacement is 0, so it's not affecting that other degrees of freedom. Here, translation and rotations are both 0, so it's only affecting to this one single degrees of freedom, which is this rotational degrees of freedom. Exactly same story for the other end. So this is displacement, y direction, this is rotation, and this is how they behave. So those are my safe functions. And this is what I'm going to use, my safe functions, to build my stiffness matrix. And I can use it to build my, well, I can express my forces using safe functions, because the safe functions, if you have a structure like this, where there's two nodes in both end, and the force is applying somewhere here in the middle, you can divide this force, which you cannot put it in the middle, to nodal degrees of freedom with help of safe functions. And it's going to be simple like this. Excuse me. So this is my safe function matrix multiplied by force. And there is a comment. So let me take a look at the comment. How you select the number of nodes? That's extremely good question. Well, this is when you're developing the elements, when you're doing this like element technology. How are you selecting the number of nodes? This is a really, really good question. What is the basis to select the number of nodes? Okay, the first. Okay, I need to admit that. Remember, I promised that if somebody is asking a question that I got confused and unable to answer, I will give you what was it. something important for each one of you. This is getting close to that. So awesomely good question. But let me try to collect my thoughts and be able to answer this. Minimum number of nodes is the nodes have to be put it in a system that the element can be connected to neighboring elements. It means that in a beam-like element, you have to have one node in both ends. In a plate-like element, like this one here, there have to be nodes in the corners because here in the corners, they can be connected to neighboring nodes. In solid elements, again, it needs to be located in the corners. Then, what about these internal nodes? Internal nodes, well, this is not so easy to answer because internal nodes, they can be considered as a way to make an element to performing better. And if you're increasing here, if you're putting here 2 internal nodes, accuracy of the element will be much better comparing element without these internal nodes. But it comes with the consequences. It comes with the fact that when you have these internal nodes, the computation will be more heavier. So they can increase the accuracy with an expense of more heavily computing. But still, this typically they increasing the number of or the order of polynomial, which is typically capable to predict more complicated behavior. So it's kind of recommended to increase internal nodes. But you can get this convergence also by increasing the number of elements. So this is, by the way, like 2 different finite element methods. So I said that you can get the better solution by increasing the number of elements. Yes, that's the one way to do it. Or you can increase the number or the order of polynomial within the one element. Those are like H and P refinement, if you look at the finite element literature. So it's H and P refinement. So they either increasing the number of elements or increasing order of polynomials. Both will bring the same kind of consequence, which is getting better solution. Now, what do you say? I'm not going to mention the name who put the comment, but are you happy with my explanation? Others, you can answer that as well, because if you're not happy with my explanation, I want to hear that. It's yes or no. Others, you're okay to answer too. I see no comments yet. Is that because of the delay or? Okay, but answer yes or no. You happy or no? No, you're not happy. You're. I got the message in my YouTube. Not receiving enough data. Not receiving enough video maintaining smooth streaming. Okay. Okay, but my question again is like, you happy or not happy? Yeah, I can do that, but it would be. I was looking for yes and no because if it would be no, that would mean that I was unable to address the question in an acceptable way, and that would be some extra points to you. But you did not answer to me, so maybe because the lower quality of the stream, maybe something else. Okay, I do have a lot of other in-class quizzes, but I was a little bit slow today. Oh, you understood. Okay, if I would be you, I would say, no, it wasn't clear. I want to have my money back. That would mean that you get some extra points. Okay, but anyways, guys, we can discuss this later in team session. All right, so what you can do in this? Where did I put my pen? Here. Yeah, not simple. Okay, so what you can do with the kinematics is that you can again build a relation between strain and displacement. And now again, you can build this relation by using this kinematic matrix B. And once you have this relation, then that's the one you can use to build the stiffness matrix. And again, the finite element modeling in a static case is this. You are solving the nodal decrease of freedom by inverting stiffness matrix. That's what it is. And so you need to get the stiffness matrix. There's one more one more comment, and it says that it's a little bit painful. It's painful, yes, I admit that. Okay, so now this relation this time will be a bit more complicated because we need to take orientation of the cross section into account. And once we have an orientation, then we know how much is a strain associated with one particular location. One more comment which I need to take a look. Acceptable but confusing. Yeah, I've got to repeat this whole thing, so no worries. No worries. Okay, so you eventually, again, error message from the YouTube, strain displacement relationship. Once you have that, then you can build your stiffness matrix. And your stiffness matrix, in case of the beam element, will have 4 rows, this way, 4 rows for columns, because you have 4 degrees of freedom. And these 4 degrees of freedom are displacement, node number 1, orientation, node number 1, displacement, node number 2, orientation, node number 2. And now this is your stiffness matrix, and that's about it. And you can also get mass matrix with help of safe functions. And this is something that is called consistent safe function, because you're comparing how the inertia is distributed, again with help of the safe function. And now finally, when moving ahead, this is how you can build the equation of motion that is describing that one particular thing we are after all the time. And we are after this U-bar, this displacement description. That's exactly what we wanted to describe. And this is it. This is where we're going to stop today. Next week, we're going to look like what is it we can do in this equation, because obviously it's going to be very hard to use the equation by simply solving the U-bars directly from the equation. Why this is going to be difficult? Well, it's going to be difficult because the dimensions of this equation is usually huge. So we can speak about 100,000 multiplied by 100,000. And we don't want to deal that many equations. So we want to reduce the size of the problem. How we can reduce that? That's going to be a super interesting story that I'm about to tell you next week. Now, with that, I can still get warnings that my streaming is not healthy. So I'm going to close this recording today, and I will send you Teams invitation momentarily. So see you in a bit in the Teams. So thank you guys, and see me soon in Teams session. All right, bye now. Oh, I need to find where's my OBS. Here it is.